Hello, welcome to Math 1960, Section 301, Calculus 2. This is UNO Summer Session 3. So in today's lecture, we are going to determine we are going to discuss about power series. We want to find the interval of convergence of power series. You want to represent a power series as a function, and we will discuss properties of power series. A power series is it's another series with a variable, and a series with variable, like this is a series. Without this x here, this is a series, but when we put the x term into it, we call this power series. This is a power series that is centered at 0. This is another power series which is centered at c. So a power series has a region of convergence and a region of divergence. We use ratio test and root test to determine, like to find out like the region of convergence of a power series. Okay, so in here we're going to discuss like few example of power series that converges. So one of them at this point is let's see. So we're going to use here the ratio test. So let's say a of n for problem number 1 is going to be equals to x raised to the power of n over n factorial. A of n plus 1 is going to be x raised to the power of n plus 1 over n plus 1 factorial. So then we take limit as n goes to infinity of a of n plus 1 over a of n. This is the way we actually find whether the series converges or not. So that is going to give me, so x raised to the power of n and x raised to the power of n cancels out, and then n factorial and then n factorial cancels out. So here I'm going to have x raised to the power of 1 over so here I'm going to have n plus 1. So that means this is like absolute value of that. It's going to be equals to 0. All right. So that means for any value of x here, my power series converges for any value of x. So okay, let's do this for this power series here. So here I have a of n equals to n x raised to the power of n over 4 raised to the power of n, and then a of n plus 1 is going to be equals to n plus 1 times x raised to the power of n plus 1 over 4 raised to the power of n plus 1. So then we say limit as n goes to infinity of n plus 1 x raised to the power of n plus 1 over 4 raised to the power of n plus 1 times 4 raised to the power of n over n x raised to the power of n. So that is going to give me limit as n goes to infinity. So here x raised to the power of n, x raised to the power of n, here we have x remaining. Here 4 raised to the power of n, 4 raised to the power of n, here we have 4 remaining. So here we're going to have n plus 1 over 4n. So times x. So then when we take the limit of that, it's going to be absolute value of x over 4. This must be less than 1 for this series to be convergent. So that means the value of x that makes the system convergent is going to be absolute value of x less than 4. Okay, so we can do the same thing here for the third one. So the third one, we have ace of n is equals to n factorial x raised to the power of n. Ace of n plus 1 is going to be equals to n plus 1 factorial x raised to the power of n plus 1. So then when we take the limit as n goes to infinity of it's going to be n plus 1 times n factorial. This we can expand it as n plus 1 times n factorial times x raised to the power of n times x over n factorial x raised to the power of n. So x raised to the power of n, x raised to the power of n, this cancels out. So then now we have limit as n goes to infinity of absolute value of x, n plus 1 times n plus 1. So this is going to be equal to 0 if x is equal to 0. X equal to 0. So this is going to be equal to infinity, x not equal to 0. So the only region that is convergence is when x is equal to 0. So in this theorem here, we want to discuss about divergence and convergence of power series. If the power series k equal to 0 up to infinity of ace of k x raised to the power of k converges for x equals to 0, then it converges for any number that is less than this. So if it diverges for x greater than x1, then it diverges for any number greater than that. And in example number 2, we have a system that converges, or series that converges at 6. That means it's going to converge at 3 as well, because 3 is less than 6. This series here diverges at 4. That means it's going to diverge for any absolute value of a number that is greater than 4, like -5, for instance. Okay, this is a theorem. For a power series, there is exactly one thing that is true. Is either this power series is either x is equal to c, okay, or the series converges absolutely for all x. We saw that. And then or there is a region that is less than infinity for which the power series converges. So sometime we want to find the radius. So the radius is going to be r at this point. We want to find the radius at which the power series converges. So we're going to say, what is my ace of n? So my ace of n here is going to be equals to x 2n over k. And then what is my ace of n plus 1? It's going to be equals to x raised to power 2n plus 2 over n plus 1. Then when we take the limit as n goes to infinity of these, we're going to have x raised to the power of 2 times x raised to the power of 2n divided by n plus 1 times, this is here x here, this should be x. So here times x over x raised to the power of 2n. X raised to the power of 2n cancels out. and then we have x, absolute value of x on this side, limit as n goes to infinity of so limit as x goes to infinity. Okay, so this is going to be n. It's going to be n here. This is going to be n, sorry. This is n here. This is n. Okay, so it's going to be n here over n plus 1. Okay, so this converges to be equals to 1. So absolute value of x equal to 1. That means the region here it's going to be equals to this is x squared for sure. This is x squared. So then the region here is between 1 and -1. So this is the region of convergence. Okay. So we want to find the radius of convergence and the interval of convergence for this power series. So we are going to use at this point the so-called the root. So limit as n goes to infinity, the root theorem. So we are going to take the root, the nth root of this. So here x raised to the power of n over n plus 2 raised to the power of 2n. Then we have limit as n goes to infinity of x over n plus 2 raised to the power of 2. That is, we have the absolute value of x, limit as n goes to infinity over of n plus 2 squared is going to be equal to 0. So for any value of x, this region here converges. So here r is in between negative infinity and positive infinity. That's going to be my r. So that's the radius is between infinity and negative infinity. So that's the region of convergence for x. So we want to define a function, all right, a power series, okay, that looks like this. The domain f is the interval of convergence of that power series. So the interval I can be evaluated at x equal to 0 by finding the sum of x of 0. So I mean, we can plug within the region of convergence. We can plug we can evaluate x of 1, x of 2 if these numbers are in between are in between the interval. So here let's see a function. This is defined this way: f of x is equal to k summation from k equal to 0 up to infinity of x raised to the power of k. Find the domain. Well, this is a geometric function, so x is in between -1 and +1. So we want to evaluate f of 1/2. So we know it's going to be, so a is going to be 1, and then r is going to be 1/2 for 1/2. So then we get 2. So then f of -1/3 is going to be a is equal to 1. 1 minus 1 is going to be over 3. That would be equal to 3 over 4. So we want to sum up these. If we want to sum up these, we usually summation of geometric sequence is equal to 1 minus x. Okay, x here being the r. So theorem of properties of series. So here we want to evaluate we want to actually